All right, welcome back. Uh, so today we want to talk about caches, continue talking about caches. Quick reminder that, the project is due tomorrow. I saw kind of half of the class almost put their numbers in. The other half, the deadline is next week. It's just, sorry, tomorrow. So, whatever you have, put it there. It's getting interesting. I see, like, I check it every day or every 2 days or so and see good numbers. I think now we are at 4 point something, which is good. I think we have two groups that are somebody beat you guys, right? So I think you were beating them, right, Audrey? What's that?
Is the auto grader?
No, the auto grader I didn't there were some issues with the auto grader. I decided not to test it, but as long as it runs on your machine, then there's no reason to be worried about it. Yeah. But yeah, let's see if somebody can beat 4.2. I think. Say it again.
It works on my machine at 0.9.
0.9.
Yeah, on my machine.
Well, I'll run it, right? You know that I'm gonna download and run those that are the top. So probably you want to be in the middle if you don't want to. Anyway, and then the next one is going to be released on Wednesday. And today's lecture actually would be mainly talking about replacement policy, which would be your next computer assignments. Any other questions before we get started? How do you like the project? So how many of you think this is a difficult project? Okay. Did you like it? Okay. All right, so we talked about memory hierarchy. We talked about kind of these optimization techniques. If you remember that we said that it's all about improving this, right? And improving the average access time. And in order to improve average access time, you need to improve the hit time, the miss rate, and the miss penalty. These are the kind of three things that we need to do. And we talked about these kind of like all these different techniques that one could use in order to optimize each group. And then I told you that's kind of like a more detailed description of these things are also in the previous videos in the past. So today I want to talk about two main things. One is the replacement policies and kind of more advanced replacement policy. And the second is the issue of when we get to the multi-core caching, how should we kind of share the cache? We're not going to talk about the kind of consistency and coherency issues that is kind of like, these are correctness issues. What we're going to talk about is how do we actually improve the performance of the multi-core systems, okay? So let's talk about the first one, and that is the cache replacement. If you remember last time I told you that a big problem in the cache is what should we do once the cache is full, right? And then if you think about it, there are kind of like, there are three important things that we need to consider. So first of all, the kind of strategies that we use in order to kind of pick a candidate, evict it and replace it with something else, which we call replacement policy. The whole idea is that we need to maximize the hit rate, right? So like, or in other words, minimizing the miss rate. If I can't do this kind of efficiently, then that's the best I can do. But replacement policy not going to solve all the problems, because no matter how well you kind of can replace things, at the end of the day, you're limited by the other factors in your system, including the size of the cache, the conflicts, and so on and so forth. Okay? So what we are really striving, what we are looking at is we need to magically pick the worst candidate, the one that's going to be furthest away in terms of usage, or least amount of hits is gonna get, right? So among the multiple n candidates, if I have this kind of magic knowledge of knowing that, okay, out of this n, this one is the least useful in terms of like getting us hit rates, then I can pick that one and hit it and evict it, right? And in order to know how well we can do this, there's actually one neat way to know what is kind of the best possible replacement policy. And that is if you actually look at the trace, okay? we don't know beforehand what is a trace. I think we don't know in future what addresses are there, right? But if I run the whole application till the end and then look at the traces, now I can find deterministically what is the best possible replacement policy, right? So if I can see that, okay, this is the pattern of the addresses that this program kind of access, then I can actually develop an algorithm that finds the best possible replacement policy for this, okay? So this is kind of the limit, the theoretical limit for how good a replacement policy is. And the good thing is for each individual application, we can find that. But now the big question is how from this, we can go to a runtime algorithm that, for example, let's say we want to pick a replacement for this. And of course, at this point, we only have this knowledge, right? We don't have this knowledge. We don't have the knowledge about the future. We only have the knowledge about the past. So using this knowledge about the past, can I predict the correct outcome? And if I can do this, then I have a good replacement policy, right? So this is kind of like the idea of a good replacement policy, and we're going to talk about various different solutions. And of course, we never can get into this best possible, but if we can get close to it, then we are happy. And by the way, there's this kind of like famous Belody algorithm that kind of like look at the traces and tell you what is the best replacement policy. If you're interested, you can do it. But as I said, this is not feasible in real systems because this assumes that you have knowledge of the future. And if you had knowledge of future, you could have done many different things. So this is kind of like what we're going to talk about, the replacement policies. And of course, the first thing that you need to know is that in order to maximize your hits, the first thing you want to do is kicking out invalid lines, right? So if you have invalid lines in a cache, then the replacement policy problem is very simple. You just find the first invalid line. What you need to do is basically the replacement policy problem is difficult when all the lines are valid and potentially useful. Now the question is which one is least useful, right? So this is what we are trying to achieve in this question, okay? Let me close these doors. All right, so there are these three questions for any replacement policy, okay? And essentially the difference between different replacement policies is how do we answer these three questions? What are they? The first thing is which one to select, right? So out of, let's say, 8 lines or 16 lines, which one should I pick? And that's basically what we usually call the select, okay? What is my selection algorithm? The second thing is the install algorithm, as in when I install the new line, so let's say, for example, out of n, I pick, let's say, j, okay? So with one algorithm or another, I pick j, and now I kick this out, and I want to replace it with this new line, let's say l, okay? So now the question is, where should I put this L in terms of the recency? Should I put it as the most recently used? Or should I put it as the least recently used? Or should I put it somewhere in between, not necessarily most recently used, not necessarily least recently used? The reason for this is that the way that we install the new line impact the future access, right? So if I put it at the most recently used, then in future, it's very unlikely that this line will be kicked out, right? So I'm assuming that if I install this new line, then it's going to be used a lot in near future. So it's a good idea to kind of keep this as much as I can. Alternatively, I can say that, okay, I'm not really sure that this line going to be used or not. So what I'm going to do is I'm going to put it as the least recently used. So I'm going to tell, allow it to kind of either kind of survive if things, goes the right way. Otherwise, it's going to be kicked out again, okay? So this kind of strategies of where do we install this is very important, as we're going to talk about a lot. Many of these different replacement policy algorithms are basically just playing and dancing around with these kind of factors of where do I install. And lastly, there is this promotion algorithm that we need to decide, as in when we have an actual hit, what should I do? Should I promote this line again to MRU, to most recently used? Should I do nothing and like whichever position it was, it is? Should I even demote it and put it in more of a least recently used, right? And based on that, again, that impact the future access, because if I put it at MRU, then we're kind of assuming and anticipating that this line gonna get more hits, even more hits in the future. If I put it in LRU, I'm kind of thinking that, oh, this line is done. We need to get rid of it as soon as possible, right? To give you an example, you're probably already familiar with this LRU, least recently used algorithm for replacement policy, and probably with random, okay? So let's actually see if we are on the same page with this. So for eviction, what do we do with LRU? Which one do we pick? Yes, we picked that's why we call it LRU. We picked the one that is least recently used. So for example, let's say we have an 8-way set associative cache. So we're gonna have 8 different blocks, right? And think about this blocks as an ordered block. Okay, so this is what we call the LRU. And this is what we call the MRU. So in terms of timeline, this is the one that we very, very recently used. And this is the one that the last time we use it. This is the oldest line in this chain, okay? What we say in LRU is this temporal locality, that if something has been used very recently, is the likeliest that it's going to be used in future. That's why if you want to kick something out, we start from the end of this chain, okay? So it's kind of first in, first out kind of scenario, right? And of course, if, for example, this one gets a hit, then what we do? We promote it to MRU. So our promotion algorithm is promote to MRU, right? So if something gets a hit, it immediately jumps up and goes to the beginning of the chain, right? And what do we do on install? So that's the eviction. When the new line, where we put the new line? Do we put it in LRU position or MRU position or somewhere in the middle? It's not anywhere. Anybody else? Yeah.
Anywhere.
Nope. For LRU specifically, we put it on MRU. Okay. So we put it as the most recently used. So we essentially, when we're adding things, we remove it from here and we put the new line at the beginning of the chain. Okay. That's usually the standard LRU algorithm. Okay. So on a hit, we promote it to MRU. On the install, we put it on MRU and we kick things out from the LRU. That's kind of usually the algorithm for LRU. What about random? So eviction, what do we do with for eviction for random? We pick at random, right? So this is just R. What do we do on install? Usually not. We actually put it at MRU. And the same for promotion. We also put it at MRU. Okay. So essentially random is usually you just pick at random at arbitrary location. Although this could be, these two could be also R and R. Okay. If you're like picking things at random, then it doesn't matter whether it goes to the MRU or not. Yeah. Well, true. That's what I just said, right? So like, you know, if, I mean, the assumption could be that you can actually have not uniformly distributed probabilities for all these, okay? But otherwise, yeah, everything would be random. The good thing about everything random is that then you're not maintaining any state. You just put everything anywhere you want. Okay. So now that we know this, let's actually talk about the actual more advanced algorithms. So in order to kind of like think about these more advanced algorithms, you know, first of all, the first thing we need to think about is the trade-off. So what is the trade-off of using a more sophisticated algorithm? Of course, the trade-off is we need more logic, right? As you can see for your branch predictor, for example, that's if you want to do more better branch prediction, you need to add more stuff. Same story for replacement policy. So you need to add more logic, more storage, which means more power, more area. And the bigger thing would be larger latency, because now I need to kind of like, query this, more sophisticated algorithm. The good thing about replacement policy is that the replacement policy is not on the critical path, right? So when we are actually loading, it's very important for us that loads kind of happens as quickly as possible, which is usually the hit time, right? And the hit time is not impacted by replacement policy. Replacement policy is when we actually missed and now we want to replace it. In that case, doesn't matter how complicated your replacement policy is in terms of performance of the CPU, but you still want to maintain some reasonable latency, because then things will back up if you don't do it quickly enough. Okay, but the big thing about replacement policy is that replacement policy improves your cache performance. Why? Because it reduces the miss rate, right? If we reduce the miss rate, then we improve our performance. So that's the important thing about the replacement policy. So you want a really good replacement policy, but you also should be mindful of your power and area kind of overheads. Okay. To kind of understand the impact of replacement policy, and as I said, not everything can be solved by replacement policy. You have to understand that essentially there are 5 different types of misses in a cache. I think if in the past, if you take my kind of introductory courses, we mainly said that there are 3, but in fact there are 5. Okay, the first one is what we call compulsory misses. Okay, compulsory misses are compulsory, as the name suggests, which means that the very first time that you are seeing a memory address, there is no way that you can cache this, okay? Because you never saw it before. It's always inside the memory. The first time you see it, then of course you can cache it. But that very first time you cannot do anything unless you do prefetching, right? So if you do prefetching or you have bigger block size, bigger line size, then for example, if I read 1, then I can bring 2 and 3 and 4 and 5 and 6 and so on. And although I haven't seen 2 yet, by the fact that I saw 1 and I either do a good prefetcher or having a better block size, then I can reduce the compulsory misses. Okay, so the big thing about prefetchers and bigger block size, as we discussed last time, is that it reduces the compulsory misses. Okay, the second thing is what we call a conflict miss. The conflict miss is just the way that we map the cache, especially because of the associativity. Okay, so if you have, let's say, a 4-way set associative cache, it means that at best all the addresses that maps into one set has 4 possible places to go. Okay, so if I have 5 addresses that all maps into the same set, then essentially if I do A, B, C, D, and E, this 5th one needs to evict one of these 4th, right? So for example, if I pick, let's say, A and then replace it with E, then if next time I see A, then this A will result in a miss, right? And the reason that we have this miss is just because the way that we structure this cache. If this cache, for example, was an 8-way set associative, then I could actually have all of these 5 in the cache, and next time that I had A, this would have been a hit, right? So just the mapping, the pure mapping of the cache would result in different outcomes of the cache, and of course, depends on how the addresses are mapped and all. But the big thing here is that the way that we, map the cache has an impact on your hit and misses. Okay, so you need, of course, if you had higher associativity or you have some these kind of like adjustable kind of associativity, then you can fix this problem. If you're interested, you can take a look at skewed cache. I'm not going to talk about it, but generally the idea is that how we can map these addresses so that it's kind of randomized or better distribution and all those things. The third one is what we call capacity misses. The capacity misses is just that, the size of your cache is limited, okay? So if you have a big memory working set and you want to map this into the cache, only a subset would be mapped into the cache. So if I have addresses here, then these addresses would be a miss, right? The solution to this is that, of course, having a bigger cache. If I have a bigger cache, then I can, put these things into the cache as well, and then reduce the amount of misses, right? So bigger cache, but then of course you can have so much, the size of the cache is also a trade-off. You cannot like have a really big cache. The other two type of misses, the fourth one is called coherence miss. The coherence is because that, one light might be shared between multiple cores. And depending on how do we kind of keep track of what is shared where, we might have more misses. Since I don't talk about cache coherency in this class, I'm not going to go through this coherence miss at all, but just keep in mind that, the way that we kind of handle what is shared with what, and kind of like have different algorithms to kind of like save that could impact your cache miss and hit rate as well. And the fifth one, which is particularly interesting for replacement policy, is what we call clairvoyance, which essentially the idea is that if I had used a better cache replacement, I didn't have this miss, or I would have that hit, right? So this is generally just purely replacement policy algorithm that if I use random versus LRU, my miss rates would be different. So this misses that purely caused by a choice of replacement policy is this fifth one. And then essentially what you really want to minimize is this fifth one, okay? So what's really, a replacement policy really gives you is reducing this conflicts and reducing this kind of clairvoyance type of misses, okay? And then another thing before, again, jumping into these different algorithms is that you have to understand there are different types of workloads. Essentially, each application might have all of these workloads. Some applications might have some of it. Some applications might have changed during the execution. So essentially, you can think about application workloads in terms of cache to be three groups. The first group is what we call cache friendly. These are applications that have lots of temporal and spatial locality, and that's exactly what we want to have in a cache system, that having these algorithms that has lots of localities, so cache can be very helpful. The big thing about these cache-friendly algorithms is that they might have a very large working set, or they might have a small working set, right? The difference between them is those that have large working set needs more cache. Those have smaller working set needs a smaller cache, right? So think about this, that for example, we do accessing an array M, and we accessing it from like address 1 to address N, okay? So then essentially, if you think about small versus big, is that if this N is a small number, then there's a small number of things that we kind of like always addressing, right? So this is a small matrix. As a result, we can cache most of it. But if this is like 1 million or 3 million or 100 million, then at some point, we're not going to be able to cache everything, right? So it's a large, working set. It still is a friendly algorithm, but with a much larger working set. And different applications have kind of these different types of behavior, okay? The second group is what we usually call a thrashing algorithms. The thrashing algorithms is those that kind of like similar to this large working set. It's a little bit different. So it's kind of like accessing a sequence of, arrays or addresses, but this sequence is much larger than the size of your cache, okay? The size of one line. As a result, what will happen is that, you might get some hits out of this if you actually manage it very well. Otherwise, they just keep, thrashing each other out, keep evicting each other out, right? So if I just kind of like, save it in this way, then the next group comes and basically this group replaces this one. Then the next group comes and this group replaces this one. By the time I reach back to this first group, it's already been kicked out of the cache, right? Alternatively, if I had a much more intelligent algorithm and maybe like kind of save some of these at least, then I could have had some hits, right? So this is very important to how to we actually kind of protect our cache from these type of algorithms. And lastly, we have this what we call streaming algorithms. These are the ones that don't have any interest in being using any sort of spatial or temporal locality. These are just streaming data into the cache without any reuse. Think about watching a video, like watching Netflix. Watching Netflix has almost zero locality because, I mean, it has spatial locality and you can kind of reduce the compulsory misses, but temporal locality horrible, right? You never actually revisit things in the past. You always move forward. You're bringing new data at every cycle. So essentially, any sort of like this assumption that, oh, the next line going to be useful, so let's actually keep it as much as we can, completely useless for streaming applications. Okay. And the last thing I want to say is that not every application is just one. Things can change during the runtime. Okay. So the application might be originally cache friendly, at some point of the program might be unfriendly and then might become friendly. So whatever you do, you cannot assume that whatever happens at the beginning might happen in the middle, might happen in the end. Okay. One thing that you will see is that for your project, we're going to give you a bunch of different algorithms, a bunch of different applications, benchmarks. And you will see that these benchmarks behave very differently. Some of them are cache friendly, some of them are streaming, and some of them are thrashing. Okay. And even within each one, there might be different behaviors. Yeah.
Trashing and streaming.
Trashing do use temporal locality. It just takes more time to go back. Streaming doesn't. It's just never reach back. Okay. So now let's start talking about optimizations. It's all about advancing our replacement policies, and with all this information that I gave you so far, now let's talk about how do we make things better. So the gold standard is LRU, right? So LRU is what we have all of us have learned in the past, and what we always do is that we kind of like keep track of the kind of the age of each block. We update the blocks accordingly, and then we pick the one that is at the least recently used place. We kick it out and replace it, and as I said, we put everything in the MRU position. That's what we do for LRU. That's kind of gold standard in cache replacement policy. So let's start talking about how do we make LRU a better system. So let's start with this question, and then you can see how we are going to go from this question. Why do you think it's a bad idea to install things at MRU?
If you ever use it once and then never again, then it's just going to sit there and pollute your cache.
Yep. So if it's you not anticipating a lots of temporal locality for that particular line in future, then you're essentially like putting it there and kind of the stubborn line gonna sit there and kind of avoid everything else to be kind of using. On the other extreme, if you put it at kind of the LRU position, you're kind of like assuming that there is almost zero temporal latency for temporal locality for this. And that would be probably less polluting idea, right? So what do you think we should do? Like, given that we have these algorithms, what do you think we should do in order to kind of decide where to put this line? Any suggestions? So now we know that putting it in MRU might not the best idea for some algorithms. For some other might be a good idea. So how do you think we should decide?
Competitive tournament, something.
Say it again.
Some kind of a tournament predictor, something.
Some form of like, make some competition and see which one works better. It's a good idea. Anything else?
Place it dead center and just say we're middle of the road at both.
Okay, so put it in the middle. Okay. It's a compromise kind of approach. Any third suggestions? These are both good ideas. The third one, anyone? Come on, guys, you're smart. It's a combination of these two. Want to say something? You always have good ideas, so maybe give me something. All right, so we're gonna see. So essentially, we can do some form of probability, right? Saying that, okay, with some probability, we're going to put it at the top, with some probability, we're going to put it at the bottom, and then use this to see how it works, right? So these are kind of like the general ideas. So let's actually talk about each one. So first of all, why it's a bad idea to put things at MRU? The reason is what we call dead on arrival lines, DOAs, okay? If you actually look at this, these are spec benchmarks. These are standard benchmarks that we use almost every time that we want to test something on any real processors. A bunch of different algorithms, each one for different things like ART, MCF, Wolf, VPR, etc., etc. If you're interested in what they're doing, these are just standard applications, okay? And as you can see, that the number of zero reuse lines are actually crazy in some of these, okay? So if you, for example, look at, if you look at something like MCF, you will see that more than 90% of the line never have a reuse. That's the definition of what we call streaming applications, right? And if we look at the average, you will see that more than 50% is actually dead on arrival, which means that really your cache is doing nothing for these applications, okay? Not only it's doing anything, it's just actually occupying some space that could have been used for something else, okay? So we need to do something about this dead on arrivals. And as I told you, there are things such as prefetching and blocking and so on that could fix it. But at the very least, we need to protect our cache from being polluted by this more than 50%, kind of behavior, okay? So what do? We do this thing called LIP, okay? So if in the past we have LRU, now let's do LRU insertion policy, which essentially what it does is that instead of putting things at the MRU position, let's actually put things at LRU positions, okay? If you're more than 50% of the time, you're not getting any reuse, then maybe it's not a good idea that whenever we want to install anything, we don't install it at the most recently used place. We install it at least recently used place. I'm actually showing it different. So this is LRU. This is so originally it was there. Now it's here, right? So this is what we call LRU insertion policy or LIP. Okay. Great things about this is that it basically means that DOA lines going to be evicted as fast as possible. So I'm really protecting the rest of my cache. So in this particular case, there are 8 of these guys. I'm really protecting these 7 from this one. And then what happens, the nice thing about this is that if I keep streaming, what I'm going to evict next time is actually this I. So I'm going to keep evicting I with the next one and next one and next one. And I retain all of these 7 all the time, which is, that's what you want in terms of streaming applications. You really retain to things that potentially are useful, and then just these things that are kind of like temporarily not going to be used, just let them just occupy the minimum amount in your cache and let them just evict, okay? So that's very good for DOA. But what do you think is the problem here? Why don't we just use LIP and then call it a day and enjoy our rest of the evening doing something else? After promoting, but it's not going to get a hit anyway, so it's not going to be promoted. So it's never actually reached to the point that it's going to be even promoted to MRU, right? It's going to be installed and quickly going to be replaced by the next line and the next line and the next line.
But what if it gets a hit and it's going to MRU and then we have stream?
Oh yeah, that's one problem. But yeah, if it's like one hit and then so it's not like DOA, almost DOA, then we have a problem. Yes. What other problems do you think if this method has? Don't think about just DOA. There are many other things as well. Yeah.
that place where we are working and we are just not doing anything with the applicants.
Well, I mean, again, as Bharti was mentioning, if this one gets a hit, it's going to be promoted here. And then you're effectively still using your entire cache. We just don't anticipate that this one gets a hit. If it does, then it goes up.
DOA type applications, so it will always be, only the idle position will be changing, right?
Yeah, but that's what you want because DOA not gonna get reused anyway. So you want to.
That type of the cache miss, right? It should be something prefetch.
Yeah, well, I mean, prefetcher is a different story. We are just talking about the replacement policy. Yes, you can use your prefetcher and bring it, be my guest. But here we're just talking about like evicting and installing. So basically it works great for DOA lines, but it doesn't work great for others. Remember that we had a bunch of different types of workloads, right? There are cache-friendly workloads, there are trashing workloads, and you fix the issue for streaming, but you're actually making cache-friendly much worse because now you're kind of doing the exact opposite of what you were expecting to happen. And what you expect to happen is that you're going to have lots of temporal locality, but then now I'm telling you that there is no temporal locality. So these are kind of competing objectives that one says, anticipate the most amount of locality. The other one says anticipate the least amount of locality. Okay, so we cannot just take LRU out and replace it with lib, because lib is essentially means that great for DOA, but horrible for everything else. It's basically very unfair to the lines that indeed do have temporal locality, because you put them into the MRU positions. By the time that they might get a hit, there might be a few other in between, and they may not even survive that, right? Versus in LRU, we put it in MRU positions. You still have like 7 or 8 accesses between the time that this one gets old. So it might actually get a hit, right? So that's the problem with lib, okay? So what should we do instead? We use this technique called BIP, which is bimodal insertion policy, okay? So the idea is that I'm anticipating that some lines are going to be useless and some other lines going to be very useful. So what should I do? I should have this kind of bimodal approach where for some lines I put them at MRU, for some other lines I put them at LRU. How do I decide that? I can start with this very simple thing. I kind of sample a random distribution based on some threshold. If the probability is like, if the number is less than some threshold, I'm going to put it at the MRU position. Otherwise, I'm going to put it at the LRU position. So for example, you can think about 50%. Then half of the time I put it MRU, half of the time I'm going to put it at LRU. But I can make this, usually this is not 50, it's usually 80-20. And 80 is usually putting it at MRU. But you can play with this number and see where is a good one. Okay, depending on the distribution of your data sets and behavior of your data set, this could change. Yes.
How to calculate the random? Random is to be random or is calculated?
Say it again.
So RND is for any random or what?
Yeah, it's just a random number generator, right? So think about a random number generator that you can have in your system, like a pseudo random, pseudo LRU, pseudo as random number generators that can generate random. In hardware, we know how to generate that very easily.
Would the epsilon here be like defined by the software?
Yes, it could be defined by software, it could be defined by hardware, depending on where this random number generation is happening.
So would it be changing with every iteration or?
Good question. Do we need to change epsilon also over time, or should we keep it static? What do you think we should do? Probably changing might be a good idea, but also it might be very hard to get it right. So typically what happens is that they put it static, which means that they look at the average behavior of a bunch of benchmarks and see where the net, where the kind of like best number is. But of course, if you can kind of figure out a good way of then dynamically deciding where to put, how to select this, then that's also a good idea. Okay. Questions?
What exactly is epsilon?
Say it again.
What exactly is epsilon?
Again, think about it as somewhere between 0 and 1 or between 0 and 100. I pick a random number, okay? And then I compare it with this epsilon, which is a threshold. So for example, if it's 0, 100, let's say epsilon is 80, okay? So any number that I pick that is below 80, then I'll do this. Any number that is above 80, that means this. So in other words, 80% of the time, I pick this. 20% of the time, I pick this.
That is the idea. And my point is, what is the rationale of behind selecting any value of epsilon? I mean, or is it also?
Oh, so the rationale is, do I want this to happen more often or do I want this to happen more often, right? So in other words, do I anticipate seeing more of streaming applications or do I streaming application or do I anticipating more of temporal locality? That's the rationale. Good. All right. So this is what we call BIP. So we start with LRU, then we go to LIP, and then we see that LIP is not the best idea, but we are kind of in the right track. So let's actually do BIP. Okay. So what is the problem with BIP? What do you think that there are modes for optimization of BIP?
An application is a combination of streaming and cache.
So if things are changing or there is combination, BIP cannot really kind of detect that. Okay, so we need something that can dynamically kind of also changes. Okay, so essentially the idea is this, that if the application is only LRU friendly or only DOA, then BIP is not a good idea, right? Because it's kind of like it's somewhere in between. Okay, so the idea is that can I actually choose, can I build a replacement policy algorithm that dynamically choose between BIP and LRU, which in this case, this is a completely LRU friendly. This is kind of LRU friendly with robustness to a streaming application. So if I can choose between these two, then I'm good to go so that I can have the best of both worlds. How do I do that? This is what we call a hybrid method, okay? So the idea is that at runtime, we kind of run these multiple algorithms at the same time and decide which one is the best, okay? So what we need for this, we need 3 steps. We need to estimate the performance of each group. So let's say we have 2, in this case, a BIP and an LRU. So we need to somehow be able to see how well BIP is doing and how well LRU is doing, okay? That's the number one thing that we need to do. The second thing we need to do is that now we need to choose this policy and apply it to the rest of the cache, right? So if it's kind of a smaller set that we are monitoring from one group and another group, then I need to somehow apply this dynamically to the rest. Basically, the winner should be used for the rest of the cache, which should be the majority of the cache, essentially, okay? So how do we do that? We're going to use this technique called hybrid methods, or later on I'm going to talk about dynamic set sampling. So essentially this is the very raw idea. It's a little bit crazy at the moment, but we're going to actually improve it. So the idea is that let's say we have policy X, okay, and then we have policy Y, and we kind of say that, okay, for each line, we're going to apply policy X, we're going to apply policy Y, and see which one is doing better, and then apply that to the rest of the lines, okay? And the good thing about this is we don't need to store, so in order to kind of check policy X versus policy Y, I don't need the data, I only need the tag store, right? I just need to know whether this address would have been existed in the cache or not. I don't need the actual data. So the amount of storage that I need is much less than a regular cache because most of the cache is actually for storing the actual data. Small part is only for storing the tag. But for detecting and kind of determining whether or not a good policy, replacement policy is a good policy, all I need is a tag directory, okay? So in order to do that, let's say I have X and Y. I originally had, let's say, X implemented. So I can have this additional tag directory, what we call auxiliary tag directory, ATD, that kind of implement the same thing for policy Y, okay? So basically I'm gonna have this, that for a set, I'm gonna have ATDX, and I'm going to have ATDY, okay? Then I'm gonna look which one is better, then I'm gonna apply that to the actual set of sets that are for the rest of my cache, okay? So how do I do that? So for example, let's say I have a counter, okay, which we usually call it a saturating counter or a SCTR. And the basic idea of this counter is this, that if both of these replacement policies get a hit, nothing changes. I just, contain the status quo. If both of them also get a miss, also we don't need to do anything because both of them are doing a horrible job. But what I do is that on kind of conflicting hit and misses, if one gets a hit and the other one gets a miss, I either increment or decrement this counter, okay? So for example, for X, if we have a hit on X and a miss on Y, I'm going to increment the counter. If the other way around, I'm going to decrement the counter. Then what I would do is that all I need to know is the MSB, the most significant bit of this counter. If that is equal to 1, it means that we got lots of these scenarios. If that's equal to 0, it means that we had lots of these scenarios. So in other words, if this is 1, I'm going to pick X. If this is 0, I'm going to pick Y. Okay? And then the rest, it basically applies with that policy. Okay? That's what we're going to do for the cache. Okay? So now the question is, what should I do? How many sets should I monitor? Should I pick one set? Should I pick all the sets? Should I pick half of the set? What should I do? And I need also to have one counter for each of these sets. So if I pick like 100 sets, I need 2 ATDs, or I need one general one general tag and then one extra tag. And also I need a big counter, right? And then how big should be the counter? That's another question, okay? So how should we optimize this? We optimize it in 2 steps. The first step is, let's say this is the kind of the sets that we are monitoring. Instead of having one counter per set, what we can do is that we have just one unified global counter, and everybody kind of increasing and decreasing this, okay? So essentially one counter per all the sets that we are monitoring. So we at least reduce the number of counters significantly, because essentially all I need is just one counter. If I get miss, I don't change this. If I get hit miss, I increment this. If I get miss hits, I'm going to decrement this, and I get miss, I'm not going to do anything, right? So this would be the strategy that we're going to use for this counter. The second thing that we're going to do is we're going to not using all the sets to make a decision, because that obviously doesn't make any sense. What we're going to do is that we're going to sample some sets. So essentially, if these are all my sets in the cache, we're going to say that we're going to pick a random 2 samples. Let's say two sets, B and E, and we're going to implement ATX and ATY only on these 2 sets. Then what I'm going to do is that based on this, then I'm going to apply this to the rest of these sets. So essentially A, C, D, F, G, and H, the replacement policy for these guys are based on the value of this counter, okay? So this way I'm going to, as long as these 2 sets, the percentage of the sample set are much less than the percentage of the non-sample sets, then I'm really reducing my overhead, okay? This is what we call dynamic set sampling, or DSS. Sometimes we also call it set dwelling, because the sets are kind of dwell with each other, okay? So there are questions such as, how many samples do we need, okay? And there are actually lots of interesting theoretical works on this. And long story short, with some number around 32 from thousands of sets, there's actually people have shown that this is enough to get the best performance. In other words, we are talking only about 2-3% of storage overhead to be able to kind of dynamically choose between two policies. Okay. The reason for this is, how many of you are familiar with the birthday paradox? Okay. Can you explain what it is? Yeah.
Something about like if you have like a group of people, then like
Mm-hmm.
they will like the probably that I can't remember it's probably or like
Yeah,
they
it's a
will
probability, yeah.
have the same birthday or something.
Mm-hmm. Yes. So if you have, let's say, a classroom that's this size, okay. If I ask this question of how many people do we need, okay, to have the probability of almost equal to 1 or 50%, I don't remember, with the high probability that 2 people in this room has the same birthday, okay, any day but the same birthday. So mine is November 6th. What's the probability of having 2 people that have the same birthday any day in the 365? Okay. What do you think is a number? Like, how many people do you think we need? We have 365 days. What do you think is a rational number to have 2 people same day? Just give me an estimation. How many of you think that? So first of all, if you have 366 people, then it's guaranteed that we have 1 day, right? That's the basic math, right? But now we are talking about probability. The high chance that there is enough number. How many of you think that there's more than 200 people needed for this? Show of hands. How many of you think it's about 100? All right. How many of you think about more than 50? Okay. How many of you think that we only need 10? All right. So the actual, you know what's the actual, who knows the actual number? It's around 20, I think 23 or 24. That's the number. It's basically square root of 365, something like, right? So essentially there is this kind of what we call this birthday paradox that essentially tells you that the probability, the high probability that 2 things happens in the same bucket is the square root of the sample size that you have. Okay. So for this birthday paradox, you need around 23 people to figure out what's to have a good probability that they have actually the same birth. So in our class, like if we have 56, there's a very, very high chance that there are 2 people that have the same birthday. Okay, we can run it on an exam day if you want to. Anybody in November in the class? We don't have November. What day?
11.
Oh, okay, we're close. This is, it also calls balls and buckets. So if you have like, another equivalent of this is that if I have n buckets, how many balls do I need to throw to make sure that I end up at least with 2 balls in the same bucket? Same story as the birthday paradox. And again, square root of that. And this problem here will reduce to that. Okay, so essentially the idea is that if I pick right samples that kind of follow the behavior of the application, I only need kind of a square root of that. And that's why this 32 kind of like comes into the play. Okay, so it's like if you have around thousands-ish sets, then somewhere around 32 is a good number to achieve that. So if you're more interested, you can actually kind of read some articles about this. I can post something for you to look at, but this is the basic idea of dynamic set sampling. Any questions? All right, so this is what we call DIP, okay? Dynamic insertion policy, okay? So dynamic insertion policy, what it does is takes LRU and BIP and assign 32 sets to BIP, 32 sets to pure LRU, then dynamically decide which one is better and applies that to the rest of the cache. Okay, so monitor both policies LRU and BIP, choose the best and apply to the rest. This is what we call DIP. Okay, questions? All right, let's have a break and then we come back and talk about the rest. All right,
Calculating the score to decide.
say it again.
How is calculating the score to decide?
How do we
Calculating the score to decide which one to use?
which one to use? It's this which one to use. So it's, if you remember, we had this counter, right? So we monitor the behavior of BIP, we monitor behavior of LRU. If BIP gets hit, increase the counter. If LRU gets hit, but BIP gets missed, decrease the counter. Look at the most significant bit of the counter. That's your policy. If it's 1, use BIP. If it's 0, use LRU. Mhm. Cool. So let's have a break. 5 minutes. We could talk. Anybody has any questions so far? All right. So we have lip, BIP, and dip. This is how dip is working, right? So we have a bunch of sets for the LRU, bunch of sets for BIP. We have what we call follower sets. This is the rest of my cache. This is my counter. Just one counter does it all. And then we look at the MSB. We use LRU or BIP, and that's it. Okay. Could be a very good candidate for your replacement policy project. Well, let's talk about how do we improve dip? Any suggestions? How do we improve dip? Yeah.
More bits to the-
Add more bits to the counter. Okay. Yeah. Well, fundamentally, like not incremental improvement, just something very different. Yeah. That's okay. You wanted to say something. Say it.
That would have, it would have, I literally do not even remember what I was gonna say.
Need more sleep, I think. Yeah.
Like use more than 2 types of chat.
Use more than 2 different replacement policies. Okay. And then how do you decide which one is the best? Like if you do 2 hits and 1 miss, how do you increase? How do you dwell between 3, for example?
It's a more bigger count. Like it's like if your first 2 bits are like something.
Mm-hmm. Okay.
Something.
Sure. Maybe for you to implement it on your computer assignments. Any other suggestions? Yeah.
We can have history register tracking that for which of the 2 was chosen. Sometimes in the last couple of iterations and then decide which. Something like that.
But that wouldn't that the counter does the same thing?
Increase the length of that. not
Increase the length. Okay. All right. Yeah, good ideas. And again, probably some good things for you to try at home. But so essentially I want you to look back at this and start thinking about so kind of like there was kind of a trick question. So yes, we can try to optimize the install as much as we can, but really dip is good enough in terms of installing. But if you remember, there were 2 other things that you can play with. The first one is how do I select which line to kick out? And the third was what should I do on a hit? Okay, and a good replacement policy kind of satisfy all 3. So far we only talked about where to install. We start with LRU and say that, okay, putting an LRU not a good idea. Then we kind of start with like doing multiple and then dynamically choosing and all those things. But that was just that middle one. So now let's talk about the first one. How do we select what to evict? Okay, if you remember, LRU was basically this timestamp machine that all it does is looking at the least recently used, it updates the least recently used, and then pick the one that is the most recently used, the least recently used, kick it out. That's the algorithm for LRU. And then, for example, if you use something dip, you can do the same thing. So you can actually, again, keep track of, timestamps and kick out the one. But when you install it dip-wise. Don't install it at memory. Okay, so don't confuse these 2. So you can still have dip with LRU eviction policy. Okay. One big thing that we usually talk in class in like our regular classes is LRU itself is very expensive in terms of implementation because you need to keep track of these timestamps and you need to update these timestamps and you need to do this for every single cache set and every single cache line. So what we usually do, and this is what we do in our real processors, is what we call pseudo LRU or PLRU. And the 2 candidates are usually what we call a tree LRU TLRU or NRU or not recently used. Okay. So 3LRU, if you're, let me see if I don't have 3LRU. Okay. 3LRU is kind of like some form of something like this. That's kind of, it's like a tree. Okay. So depending on the bits, you kind of like go up or down. And then you pick the line that you want. Okay. And this is usually the kind of history or the flag bits. The NRU one is the one that typically people are using and looks something like this. So let's say I have a 4-way set associative cache. On the left, what I'm showing is the regular LRU. And on the right, I'm showing you NRU or not recently used. Okay. The difference between LRU and NRU is LRU has 4, let's say in this case, it has 4 positions. This is the most recently used position, which usually go 4, 3, 2, and 1. These are the positions that we have, right? NRU has only 1 bit, either 0 or 1, okay? Initially, when everything is invalid, okay, everything is 1. So flag bits are equal to 1, okay? In LRU, you just put things invalid, okay? So this is the initial position of NRU and LRU. So let's see what happens next. So let's talk about LRU. So let's say I have the sequence of addresses of A1, A2, A2, A1, B1, B2, B3, B4, A1, A2. This is the sequence of addresses, okay? So let's see what happens with LRU. So A1 comes and every line in my LRU is invalid. Of course, this will result in a miss. Then what I do is that I put my A1 into the MRU position. Let's say this is the classic LRU. It's not DIP, okay? In DIP, we wouldn't do that. But in classic LRU, we are putting it at the MRU position. Now A2 comes. A2 is also miss. We put A2 in the MRU position. As a result, A1 goes 1 step down. And remember, until we have invalid lines, we have no question about what to evict. We always evict the invalid lines. So I continue doing this. I get A2 again, and then I get A1. This is where I'm going to get 2 hits, right? And then at this point, I have A1 as my MRU, because on hits, I promote the line to the MRU. So that's why at this point, A1 is the head of the chain, okay? Now B1 and B2 comes, right? And these 2 guys are shifted to the right. So I have at this point here, I have B2, B1, A1, A2, okay? Now B3 comes, and this is where we are going to use our replacement policy. This is where we need to make a decision of what should I evict. What do I evict in this case? I evict the one that is in the LRU position, right? So I evict A2, put B3, and shift everything to the right. And then I continue doing that. B4 comes, I kick out A1, but now A1 comes, and because we made a mistake and we made a bad decision, now A1 is a miss, right? And then we're going to actually address this in future. But this is generally what is wrong with the bad replacement policy. If you evict things incorrectly, then you're going to have unnecessary misses, okay? So this is just a classic LRU, nothing new about this. Let's see how NRU works in this case. In terms of hit and miss patterns, what we're going to show you is that you're basically going to get a very similar hit and miss rate. And that's kind of the goal of MRU. But the nice thing about NRU is it only uses 1 bit per position, versus this one requires timestamps. It requires 1 and 2 and 3 and needs to update things and move things and all those things. There's no notion of chain in NRU. So how does it work? So initially everything is 1 and everything is invalid. Then A1 comes. Let me use a different color. A1 comes, and what we do is that we pick the first invalid from the left and replace it with that. So we put A0. Another thing that we do on install, we flip the flag from 1 to 0, because 1 means not recently used, 0 means recently used. So we put it equal to 0. Then I'm going to continue doing that for A1, A2, and then A1, A2, and then A1, A2. Remember that positions doesn't matter in NRU. So all the positions are the same. So there's no switching going on in NRU. All right. Then B1 comes, and again, I put B1 here. Then B2 comes, I put B2 here. At this moment, everything is full and all the flags are equal to 0, okay? So when this happens, we immediately restart all the flags back to 1, okay? This is the algorithm that we use in NRU. At this point, everything becomes 1, 1, 1. Then B3 comes, and I put B3 where? So when everything is 1, okay, I search from the left and pick the first one and kick it out. From the left, pick the first one, kick it out. In this case, is A1. So I put B3 and then make it 0. Okay. So now I have B3 with 0 flag. Everything else is with 1 flag because everything was reset. Now B4 comes. And again, B4, I need to kick something out because everything is valid. I need to pick something out. What do I pick? I start from the left and I pick the one that is equal to 1. In this case is A2. So I pick kick out A2 and put B4 and I put 0 flag here. Now again, same issue as LRU. We unfortunately kicked out both A1 and A2. So what should we do now? We put A1 in the first flag that is not equal to 0. This is B1. We put it B1. Then we put A2. And then again, all of them become 0. At this point, we reset and we continue. Okay. What's the difference between these two? Performance pretty much the same. Nice thing about NRU is that you only need 1 bit and you don't need to update any position. Much faster. And that's why we implement usually NRU in our real processors, not LRU. LRU in some cases, of course, do a little bit better, but people have shown that we are within 90% of the accuracy of LRU with just NRU. This is also another thing that you could try when you do your computer assignments. Use NRU and LRU and see which one is faster. Yep.
So I understand that this is for replacement and the other one was for actually inserting into the cache, but how would they interface with each other if this is just a 1-bit on?
If it's 1 bit, then you cannot do all those tricks that we talked about.
Right.
But we're gonna actually get to that point. Yep.
NRU is just different in terms of the storage, right? It's updating the storage.
Storage and updating, so you don't need to also update things, right? Update is just 1 flag that you need to reset. But LRU, you need to essentially move these guys around.
Yeah, so it's not that we have any new idea or technique to
No,
improve the section.
no, it's just you're saving in terms of storage. So you're kind of trading a little bit of performance with a little bit of storage. That's really what you do. Okay. So this is NRU. And the reason that I'm talking about NRU is that we want to improve NRU, and you kind of like we are on the right track. So how do we improve NRU? So essentially with NRU, the usefulness, the reason that we kick things out is a binary decision of 0 and 1. Things that are 0, we don't kick out, we keep. Things that are 1, we kick out. If everything becomes 1 at the same time, then, everything becomes 0, then everything became 1. So it's kind of like limited in terms of decision making. Things are either useful or not useful, right? So obviously an improvement to this is adding a little bit of more option to each one of these. So the immediate things that we do is we are adding what we call a re-reference interval prediction counter, or RIP, okay? So what is a RIP? RIP is essentially the glorified version of NRU, a more bits per cache line in order to kind of track whether things are useful or not useful, okay? So how many bits? This is again the question similar to the branch predictor question. People have looked at it. 2-3 bits is usually a kind of good balance, okay? And then when we are talking about RIP, then of course we need to kind of talk about where to install things in RIP. And we have the same old question that should I put it in MRU or LRU or somewhere in the middle? And what should I do in a hit? This is what we call the RIP replacement policy, okay? So 2 options. And option number 1 is what we call SRIP. SRIP is the static RIP, okay? So what it does is basically giving you this option that you insert on 2. Okay, so first of all, this is a 2-bit number, so your numbers are 0, 1, 2, and 3. Okay, 3 is the old one, and 0 is still 0. Okay, so the higher the number, the less useful it is. So 3 means I don't like it at all. 0 means that it's very useful. Okay, so where do we install? First of all, we can actually install it wherever we want, but we install it at 2, not 3, to kind of like, balance between not completely MRU and not completely LRU. Okay, so we put it on 2. We promote to 0 on a hit. So we always, again, similar thing that we did in the past. If it's get a hit, we put it MRU, and we evict on 3. Okay, so 3 is again our kind of LRU position. Okay. If all of them are, if there is no 3, we do the same trick that we did with NRU. There we reset everything to 1. Here we just increment by 1. We don't just completely go all the way to 3. We just increment everything by 1, which we call aging. So we age things, we go it 1 level up. Okay. So if you look at the same example that we had, everything originally started with 3. Then a new line comes, and now you can see we put at 2. Then again, the next line comes, we put at 2. Then we have a hit, and if we have a hit, we promote it to 0. We have another hit, we promote it to 0. Then we have another line, B1 comes, we put at 2. Another line comes, we put at 2. Okay. Now we have this situation that all the lines are valid, and we need to kick things out. Which one should we kick? We should find the one that is equal to 3. None of them is equal to 3, so we need to age. So we increment all these by 1. So you get 1, 1, 2, 3, 3, 3. Okay. Then we start from the left and we pick the first 3. In this case, this one. So this one is kicked out and replaced by B3. And we put it at location 2, right? So we put it at location 2 because every new line installed will be 2. Now the next line comes. And sorry, not the next line. I think at this point yeah. So the next line comes, and this is B4. Which one should I evict? I should evict B2. I replace it by B4. Okay. And now this is where A1 and A2 comes. And as you can see, RIP is doing much better job than NRU and LRU, because now I actually kept A1 and A2. The reason for it is that I kind of add a little bit more hysteresis usefulness to the lines. Since I had hits for A1 and A0 here, I kind of remembered that and didn't kick them out. Instead, I kicked a B1 and B2 out to replace it with B3 and B4, right? So this is kind of like the big difference between RIP and LRU and NRU, okay? And as you can see, the overhead is still very manageable compared to LRU because I essentially just needs 2 bits per line. I don't need that crazy updates. I don't need to have a chain and all those things. Okay, so very simple and very straightforward. And this is what we call RIP. And then these values are called a re-reference value. I don't remember. Prediction value, something like this. Re-reference prediction value, or RRPV. Okay. And then algorithm is also described here if you're kind of not sure about what we did. Any questions about strip? All right. So how do we improve strip? We did the same trick that we did with BIP with strip. Okay. So if I don't know where to put my line, right? Should I do it at 2 or should I do it at 3 or should I do it at 1? What I'm going to do is that I'm going to dynamically decide. How do I dynamically decide? I do dynamic set sampling between BIP and strip, and then that's what we call DRIP. Okay, dynamic re-reference inference prediction, something like that. Okay. So essentially what I can do is that, first of all, I can just do a regular BIP. That is, I put most lines at 2 and some lines at 1. So this is what we call a BRIP. Okay. So this is the same as lib and LRU. So remember lib and LRU that we had some probability and we call that BIP. So what I can do is that instead of doing always 2, I can with some probability sometimes put at 2, sometimes put at 1. I call this BRIP. Then between BRIP and SRIP, then I do DRIP. Okay? So I'm making a song out of this. All right? So how do I choose between SRIP and BRIP? I use the dynamic set sampling, and who is the winner is the one that I'm going to use. You had a question, sorry.
And the previous algorithm.
Uh-huh.
Rip,
Uh-huh.
there was no 3 and there's a miss.
Mhm.
You're just aging, you're not replacing any of them.
Yeah, you do. You age and then you find the first 3 and then you replace.
So there's no case where it's you age and there's still no 3.
Oh, then you age again.
Okay.
Yeah, you keep aging. So it's a loop. Actually, if you look at this, it's search for first 3, then and then if 3 found, go to step 5. Otherwise, go back to step 1. So it's kind of a loop that you keep doing until you find the first 3. So it might be a scenario that all of them are 0, so you have to do it 4 times until you find your 3. All right. So again, SRIP is you always put at 2. BRIP is when you with some probability you put at 2 or 1, and DRIP is dynamic set sampling between SRIP and BRIP. Okay? Does that make sense? So are there more? Yes, there are. So we didn't talk about what to do on a hit. In all of these algorithms that I talked about, we always promote to MRU on a hit. But guess what? People have thought about what we call a PIP, which essentially what it does is that don't promote it to all the way to the MRU. Maybe it's better to kind of put one position before MRU. And if you're really going to use it, then put it on a hit. And there are many more. If you're interested, start with PIP and then look at some others. And again, I'll leave you guys to kind of like do your own research for the computer assignments. And as I said, the computer assignment would be about this replacement policy, very similar to the first. We're going to give you a framework and a bunch of data sets. You have to implement a replacement policy algorithms that reduce the miss rate. Okay, so we want to minimize the miss rate as much as possible. And again, we're going to have the table and leaderboards, and whoever has the lower miss rate would be the winner. We're going to give you LRU implementation and I think SRIP implementation already there. You can start optimizing those in order to achieve what you want to achieve. Probably some form of dynamic set sampling combined with some improved version of DRIP and SRIP. This is probably what you want to do. Okay. Questions? So names are a little bit confusing, but general idea follow that, right? So where to put, how do I dynamically choose, how to evict, and how do I dynamically choose? These are the main 2 things that we really did. Okay. Cool. All right. So we don't have much time left, but let me at least start this part and then we're going to finish it next time. So the second thing I want to talk about today is that, so first of all, we talked about this. I want to talk about multi-core caching and the problems that we have and generally how do we share, because all these things that we said so far is for one application. One application comes, how do I replace, how do I promote, and all those things. But what if there are multiple applications? How do I decide then? Okay. And then if you remember that we already said that everything is hyper-threaded superscalar, which means that at any given time, there are multiple applications running on your system. So you never have just one application. You have to be careful about multiple applications. Okay. So we need to kind of decide, and we need to do it dynamically, how to share my cache between these 2 applications or these many applications. And if you remember in old days when we were talking about multi-core systems, if you haven't seen it, that's fine too. Generally, you have 2 options to share cache. Okay, you can have what we call a private cache, which essentially, if I have, let's say, 4 cores, each core can have just one cache for its own, doesn't share anything with anybody else. or you can have one cache that is shared among everybody else, okay? This is usually what we call a shared cache, and this is what we call a private cache. So everything is private to each core. What are the pros and cons for each one? Anybody wants to suggest? What's the pros? Mm-hmm. Mm-hmm. Mm-hmm.
Streaming applications. shared
Is it better? Why?
Because we have like access to all locations at the same time. It's not like it's dedicated. If some part of the application requires more memory
Mhm.
space, and some part requires less.
Mm-hmm.
It's not like restricted.
Mm-hmm. Okay. So better utilization in some sense, right? Mm-hmm. Anybody else? Yeah, they're kind of like, in the right track. So there are two things I want to kind of like, specifically mention. One is the hit time, and the other one is kind of miss rate or utilization. Hit time for private cache is significantly better. The reason for it is that it's directly connected to the CPU, so the interconnect is much, much faster. That's why usually for L1 and L2, we don't even think about sharing it, because sharing it immediately reduces the hit time. And since L1 specifically, the hit time is very important for us, we never share it, okay? But good thing about shared is utilization, because again, going back to the idea of fully associative versus direct map, I told you that, if it's kind of a free for all kind of situation, then you can have a better utilization, space utilization for a shared cache, versus if it was private, if one application doesn't really use their cache, this additional space cannot be shared with the other cache, right? But if it's shared, then you let them dynamically decide. So that's a good thing about the shared cache, okay? So kind of the advantages and disadvantages. So for shared caches, good thing is that it allows you to do dynamic partitioning. There's no fragmentation. If you, again, coherence policies are much easier to maintain, and it's easier to share data, because if you wanted to share and everything was private, then it goes to one cache and then comes out of the cache, goes to another cache. So it's kind of ping-ponging between them. But if it's a shared cache, it's just one location, everybody access to that location. The bad thing about shared cache is now the performance of one application impact many others. So think about streaming application, actually. Streaming application, we told you that horrendous for cache. I'm now thinking about this dominant alpha application that wants to hog the entire cache. So everybody else, even the poor cache-friendly application, is now penalized by the fact that there is this gigantic streaming application that just occupies the entire cache. Okay, so this is kind of a big problem for us, that a bad application can essentially destroy not only the performance of themselves, but many other, because now it basically kicks out not only its own data, but it kicks out everybody else's data. Okay, so this is a big problem with the shared caches. Okay, so now the idea is, how do we share the cache, given that we have this idea? There are two main things that we can think about, right? The first thing is that, okay, let's equally share it. Like if I have 4 applications, 1/4 of the cache is one application, 1/4 for the other, 1/4 the other, and so on and so forth, right? The second is free for all. If the whole idea is allowing the utilization, let them fight it out, right? It's free for all kind of like, a situation. If somebody wants more, give them more. But what is the obvious problem with this? The obvious problem with this is that cache demand is not equal to cache performance. That again, if there is a streaming application or a thrashing algorithm, they might need more cache, but they're not really improving better, because they're not supposed to even use cache. Okay, so that's the kind of like significant problem when it comes to the sharing. In one hand, you want to share, while on the other hand, you have to be very, very careful of these bad actors. Okay. So how do we do that, and how do we fix this problem? The idea is, one idea that we're going to talk about is what we call utility-based cache partitioning. Okay. So the fundamental insight is, if I can somehow predict who is benefit the most from getting more space, then I'm going to give it to that. Okay. If someone is not really performing better by getting more, I'm not going to give more space to them. So it's kind of a monitoring strategy that will look at who might benefit from more space. We're going to give it to them. So it's not like if you ask it, we're going to give it to you. It's more of like, if you really benefit from it, we're going to give it to you. Okay. This is what we call utility-based cache partitioning. Okay. Or UCP. So two main questions. How do I track who is going to benefit? And then how do I partition once I know that? Like, because now I need to kind of dynamically move around things. So these are the two fundamental questions for utility-based cache partitioning. So first of all, the motivation is, if I look at kind of three types of applications, and again, these are three spec benchmarks. You see that there are some, so x-axis is showing the number of ways. So think about, we are partitioning the ways. Okay, so let's say if this is a 16-way set associative cache, and we have a bunch of different algorithms, we want to see how many ways should I give to each application. Okay, so I'm going to basically sweep from 0 to 16, and now want to see how the performance of the system changes as I assign more ways to this cache. Some applications have what we call low utility. They don't care about how much ways do they have. These are the applications that either they are streaming applications, or they have so many compulsory misses. Okay, doesn't matter how much you want to they get. So these are the ones that you should avoid giving space, because they're not going to use it properly. So we should minimize their access to the cache. On the other hand, we have these green applications that the more they give them, the better they're going to perform. So these are what we call high utility, that they can genuinely benefit from getting more ways and more space in the cache. Okay. And then there are some that are kind of in between, and these are what we call saturating utility, that for some, if we give them some more ways, they can improve, but more than that, it's saturating. They don't care more. So they need, for example, I don't know, 4 or 5 or 6, but between 6 and 14, there's no significant difference. Okay. So what you really need to do is kind of identifying these three applications, types of applications, and then dynamically decide which one to give. And then we basically define utility UBA is, we basically define it this way, that if I have A ways, A as in alpha, minus B as in beta ways, this is the utility. So for example, for this low utility, this number is very close to 0. That's why we say low utility. For this green one, this number is huge. So this is high utility. And for this one, for some regions, this number is big. And for some reason, this number is regions where this number is small. That's why this is what we call saturating utility. Make sense? So how do I do this? I need something like this, that if I have a bunch of different cores, okay, what I need is, I need monitors to look at each core and try to kind of estimate how much utility do I have. So if I have what we call a utility monitor, which I'm going to explain later, and then I have it, and then this utility monitor basically feeds into this partitioning algorithm, then what I can do is that then based on this partitioning algorithm, I can partition these caches. Okay. So I need a bunch of monitors, utility monitors, to see how the cache performs if it gets more and less ways. And this needs to be done in a dynamic fashion. Once I have that, I need to apply to some partitioning, saying that, okay, based on this utility monitors, it seems that application A needs a lot of ways. Application B is kind of like oblivious, and application C could use a little, not much. So this is how I'm going to partition. I'm going to give most of the ways to A, almost minimum to B, and a little bit to C. That's how I'm going to partition this application. Okay. So how do we implement that? Let's actually talk about this next time we talk about on Wednesday. Okay. Any questions? All right. So see you guys on Wednesday.